Hi, in this video we are going to take a look at a technique called two-phase method, and we will demonstrate it with a simple problem. When we are dealing with the simplex method, when all of our constraints have less than or equal sign, we have a natural extreme point, which is the origin. However, when some of these constraints have greater than or equal sign or even equal sign, then we do not have that luxury. This is an example in which you notice that origin is not a feasible extreme point of the problem. For the two-phase method, there are a set of steps that we have to take. It's a simple process, but it requires you that you pay attention to each step separately. We are going to take a look at these steps in its order as we go through the problem. The first step in two-phase method is to convert the problem into a standard form. I have set up a small maximization problem with 3 variables and 2 constraints. All variables are greater than or equal to 0, and the 2 constraints, one of them is less than or equal sign and the other one is greater than or equal sign. The first step in two-phase method is to convert the problem into a standard form. In here I have added a slack variable to the first constraint and subtracted a surplus variable from the second constraint. The z function has also been converted into a standard form, with the S1 and S2 being added to the non-negativity constraints too. Now that the standard form of the original problem has been accomplished, we need to start the phase 1 of the problem. In this case, first of all, we're going to add artificial variables . There's only one artificial variable needed for this small problem, and that's on the second constraint. We will add artificial variable. We will change our objective function for the phase 1 to the summation of the artificial variables. And just because in this case we just have one artificial variable, it would be just R1. If we had 2 of them, it would be R1 plus R2, and so on. The objective function of the phase 1 is a minimization. So in this case we are going to be writing minimize z prime to just distinguish it from the original z, minimize z prime to be equal to R1. We will convert that into standard form, so R1 will come to the left side of the equation and set everything equal to 0. So we will have z prime minus R1 equal to 0, with x1 plus x2 plus 2x3 plus s1 equal 10, and 2x1 3x2 plus x3 minus s2 plus R1 equal 8. x1, x2, x3, s1, s2, and r1 all being greater than or equal to 0. Now this is the place that you can actually accomplish the things in 2 different fashion. You can do the part outside the tableau. I personally put them inside the tableau. It's easier for me to manage it because it's just a case of copy and paste for later tableaus. So I have set up the first tableau, and then I noticed that this tableau is not a legitimate tableau because R1 in this case is basic variable, but At the Z prime row, the entry under R1 is not 0. A legitimate tableau has the basic variable associated with a column of the identity matrix. So we need to get rid of that -1 under R1 in Z prime row. To do that, simply we are going to multiply the R1 row by a +1 and add it to the Z prime row. The next legitimate tableau now will have 0 under R1. Remember that this is a minimization problem, so when we look at the Z prime row, instead of searching for the most negative, we are now searching for the most positive. In this case, the entry under x2, which is 3, indicates that x2 is the entering variable. Calculating the mean ratio, 10/1 and 8/3. 8/3 is the mean ratio, so R1 leaves the basis. As soon as R1 leaves the basis, we will have our next tableau generated through the regular simplex. We will have our next tableau generated through the regular simplex, and in this tableau we will have S1 and X2 as basic variables. We process the regular simplex iteration and we would end up with an optimal solution for this phase 1 objective function. Z prime is going to be 0, x1, x3, s2 and r1 all be 0, non-basic. S1 will be 22/3, x2 will be 8/3 with the z prime 0. This is of course a feasible solution because there is no artificial variable in the basis. So we will declare the end of phase 1 and beginning of phase 2. In this case, at the start of phase 2, we are going to replace the original objective function. The original objective function into this tableau. We will drop the artificial variable column from the tableau. The original objective function was this objective function here. So we are going to add this into the new tableau. Z minus 3x1 minus 4x2 minus 2x3 equals 0. And that is what we have in here. Minus 3 minus 4 minus 2 and 0. At the start of phase 2, we will notice that the created tableau is no longer legitimate tableau because x2 is a basic variable and its entry under the z is not 0. Just like start of phase 1, we are now dealing with the same situation. So we are going to multiply x2 row by 4 and add it to the 0. That will generate a 0 in here, and we will have a legitimate tableau. This is a legitimate tableau, but it is not optimal tableau. Remember, Now that we have returned to our original problem, and our original problem was a maximization problem. So now at the zero, and then we are going to find the most negative. In this case, minus 4 over 3 is the most negative entry at the 0. So we are going to process that as entering variable. This entry is negative, so we are not going to calculate any ratio, any critical ratio for that. And so the only option is S1. S1 will leave the basis, and S2 will enter into the basis. As we process that, we will end up with a final tableau and the final solution. In this case, solution is x1 and x3 and s1 equals 0, s2 value is 22, and x2 value is 10, with the z value optimum to be 40. This is a very simple process. It has everything that regular simplex has. The only thing that we do in this case is to break it down into two phases. One deals with the minimization of the artificial variables, and the other one with the actual problem, whatever the objective function is, whether it's minimization or maximization. Remember that there are two things that might happen. First of all is that we will end up, in this case we ended up with a optimal solution for phase 1. What happens if you end up with an optimal solution for phase 1? What happens if you end up with an optimal solution with the phase 1, but in the basis you would have r's? If artificial variable exist in the basis, we will not most probably have a feasible solution. If those artificial variables which are in the basis are going to have right hand side values greater than 0, then you will not have a feasible region at all. However, if they exist here but their values in here is 0, if they exist in here but their values in here is 0, then you do have a feasible point. However, look at this last line in here which says drop artificial variable column from the tableau. In that case, you cannot drop that artificial variable column from the tableau. But if in the following steps artificial variable leaves the basis, then you can drop that column. That's it. It's a very simple process. A little practice and you will get everything done very easily. Of course, regular problems have more than one artificial variable, but it doesn't make any difference. The process is the same.